show you. Normally we do an actual summative reaction with this, where you get to carry out the experiment. So let's just walk through one on paper. I'll give you what some of the lab errors would be if you were to do the experiment, and then we'll be done with this. Okay, so here's a lab situation you might carry out. You've been hired as a chemical technician, and you've asked to carry out a quantitative analysis. That just means analysis using calculations. And you want to isolate a precipitate. So this is going to be a precipitation reaction. So you're going to react 0.50 grams of nickel nitrate, which is going to be your limiting reagent, but you also need to know how much excess reagent you're going to weigh out. So this 0.60 grams is more than what you need to fully react the 0.5, but nonetheless you have to measure it out because you need to have some nickel nitrate reacting with the excess reagent, the sodium hydrogen phosphate. So what we're going to do is exactly what we just did, the 3 steps. So we're going to take nickel 2 nitrate, NiNO3, and we're going to react it with sodium hydrogen phosphate. So hydrogen phosphate, if you go to the back of your periodic table, is HPO4 2 negative. Okay, so this is a +1, this is a 2 negative. So we need the 2 sodiums to balance that. It's aqueous. We're going to do our double displacement swap. So the nickel is going to pick up the sodium hydrogen phosphate. That's our precipitate. And then the sodium is going to pick up the nitrate, and that's our supernatant. So this is our LR. This is what we're solving for. The mass of LR we're given is 0.50 grams. This is our excess reagent. This mass is 0.60 grams, but we're not using this because it's the limiting reagent that determines the theoretical yield. So before we start, we need to balance this equation. We have 2 nitrates here and 2 sodiums, so we need a 2 over here. Okay, so first step is you're going to find your moles of your limiting reagent, your nickel 2 nitrate. So moles is little m over big M. The little m is 0.50 grams, and your big M, let's calculate that over here off to the side. So M of NiNO3 2. So the molar mass of nickel is 58.693. We have 2 nitrogens of 14.007. And we have 6 oxygens at 15.999. We're going to plug that in our calculator, and we're going to get that molar mass, and that molar mass is going to be 182.701 grams per mole. So we're going to plug that in here, 182.701 grams per mole, and when we punch that in our calculator, we get 0.0027367 moles of nickel nitrate. So now let's do our mole ratio. And our mole ratio is going to be of LR to product. Okay, so we're going to take the 0.0027367 moles of LR, which is nickel nitrate, and we're going to multiply it always by product over limiting reagent. So 1 mole of nickel hydrogen phosphate divided by 1 mole of nickel nitrate. So it's a 1-to-1 relationship, which means now you're going to get, when you take this, multiply by 1, divide by 1, it's the same number, 0.0027367 moles of nickel hydrogen phosphate. Okay, so that is the moles of our product. So the last thing we're going to do is get our mass, and then that's our yield. So find our mass of nickel hydrogen phosphate. So mass, remember our formula, is moles times molar mass. Well, we have the moles. now we need our molar mass. So what we're going to do is calculate that over here. So we want our molar mass of NiHPO4. So we have 58.693 is the molar mass of nickel, 1.008 is the molar mass of hydrogen, and then we have the molar mass of phosphorus, which is 30.974, and then we're going to add that to 4 oxygens at 15.999, and when we punch that in our calculator and add it all up, we're going to get 154.671 grams per mole. So that's what we're going to put in here, 154.671 grams per mole. And it's kind of squished in there, but when you punch that in your calculator and you look at significant figures, you want 2 sig figs, your answer is 0.42 grams. Okay? So what that means is if you carried out a perfect experiment where all 0.50 grams of nickel nitrate was used up, you should produce exactly 0.42 grams. So how do you do the experiment? Well, so just explaining the steps is you're going to have 2 beakers. In one beaker, you're going to measure out the 0.5 grams of nickel nitrate. In the other beaker, you'd measure out the 0.6 grams of nickel nitrate, and then you're going to add a little bit of distilled water. Why distilled? Because distilled water doesn't react with anything. Okay, so you're going to add some distilled water to each beaker, and you're going to stir those solids until they're fully dissolved. Okay, absolutely fully dissolved, no crystals left. And what you'll notice when you stir them is your nickel nitrate solution is going to be clear and green. Okay, if I had some here, I'd show you, but I don't. And your sodium hydrogen phosphate solution is going to be clear and it will have no color at all. So we're going to say that it's colorless. Okay, the mass of limiting reagent that produces our product is the 0.5 grams, because remember, nickel nitrate is our limiting reagent. So now that you have your 2 beakers and they're dissolved, and you record their colors, all you're going to do is pour one into the other and let them react. Rinse out the beaker you just emptied really, really well, so everything is in that one beaker. Give it a good stir. It's going to look like thick soup because there's precipitate in there. And then we've all done filtration before. This time though, you're going to take your filter paper and you're going to measure its mass. So let's say our mass is 0.87 grams, which is a typical mass for a filter paper. You're going to fold it in half again, put it into your funnel, wet it a little bit, and then you're going to take that those contents of that beaker that has your precipitate and your supernatant in it, you're going to pour it through your filter paper and rinse out your beaker really, really well and just let everything filter. Once it's all filtered, your precipitate will be collected in your filter paper, but it needs to dry. So we're going to let it dry overnight, and then the next day when we come in, we're going to take that filter paper that has your dried solid, we're going to put it on the balance, and when we do, we are going to get a mass of 1.25 grams, for example. So then how much precipitate is made? Well, what you're going to do is take this and subtract it. So you're going to take the 1.25 grams, which is your paper and your precipitate. You're going to subtract the 0.87, and you're going to get 0.38 grams of precipitate. This is your empirical yield. So we should have got 0.42, but in our lab we got 0.38. That's not bad. That's a pretty good result. Okay, so what you're doing is filtration. You do your double displacement reaction, your reactants in separate beakers initially, record their colors, pour one into the other, mix it really, really well, and then just filter it like we did when we did our precipitation reactions in our reaction unit, and let it sit. Okay. After your precipitate is dry, it will be on that filter paper. So what you can do now is weigh it and subtract it from the filter paper, and that just leaves you the mass of this. Then you can describe it. So the precipitate for this, it's a solid, it's green, and it's crystals. Okay, and then the filtrate is what is in your flask. That's where your supernatant and your wash water is. That is clear, and it's colorless. Okay, all right, so now what we want to do is we want to determine our percent yield. So remember, percent Y is EY over TY times 100. So our EY is going to be the 0.38 grams. We're going to divide it by the 0.42 grams times 100. And when we do, we are going to get something less than 100. We're going to get 90. And we want 2 sig figs. So because we get 90.476%, 2 sig figs, we need to cut it off. So 90 decimal percent. So guess what? We are right on the effective amount. So we can say yes, effective. And that's because it's between 90 and 110%. We're right on that 90. So we had a really good experiment. One thing, just to refresh your memory on how to do this, your Ti and Ni. So if you have Ni, NO3, 2, plus Na2, HPO4, aqueous, and you get NiHPO4, solid, plus 2 NaNO3. What we want to do is we want to, because remember we have a filtrate that has supernate. Supernate are spectator ions, so we want to determine what those spectator ions are. So we're going to do our total ionic equation here. So you're going to break this up into Ni2 plus. We have 2 nitrates, 2 NO3 minus. We're going to break this up because it's aqueous. We have 2 sodium ions. We have 1 hydrogen phosphate ion with a 2 negative charge. We leave our solid intact because it's not aqueous. And then we're going to split this up into 2 sodium ions and 2 nitrate ions. Okay, so now what we'll do is go through, identify our spectator ions. 2Na, 2Na, 2NO3, 2NO3. So our net ionic equation is the nickel ions in our nickel nitrate reacted with the hydrogen phosphate ions in our sodium hydrogen phosphate, and that produced our precipitate. So that's what that looks like. So what do we have? We have a flask. Inside our flask we have a funnel. Okay, so this is our funnel. This is our flask. Inside the flask we have filter paper. Okay, in here we have our green precipitate. Okay, so this here is our precipitate. Okay, and then what's in here? Well, this is called the filtrate. So what we have in here, remember, we have wash water because we rinsed out our beakers and our stirring rods. We have the supernate, which is the same thing as our spectator ions. So what are those? So that's our 2NO3 minus and our 2Na plus. But what else is in here? There's also something else in here. Our nickel nitrate fully reacted. So this fully reacted. But this here is our excess reagent, which means it didn't all react. So we also have our excess reagent ions in here. If this is our excess reagent, these are the excess reagent ions. So we also have some of those in here. So some 2Na plus and some HPO4 2 minus. Okay, so it's really important that you recognize that whenever you do a precipitation reaction, one of your reactants will always be left over. And those ions, when you do your tie and nye, if this is your ER here, these are your ER ions. We know that because we just split it up. They are also in there. So now we have there's three things in our filtrate. Our wash water, our supernatant, which is our spectator ions, and our ER ions that are unreacted. Some of them did react until all the nickel nitrate was gone, and then those ions left over are the ones that are in there. So this is really important. Expect a question about that on your quiz. So how do we know that the nickel nitrate was the limiting and the sodium hydrogen phosphate is your excess? Well, you have qualitative proof. Your precipitate, okay, is green, and your nickel nitrate is green, okay? Your filtrate was colorless, and your sodium hydrogen phosphate solution was colorless. How do we know that? Because we wrote it over here. So we produced some nickel precipitate, which is why it was green, and our filtrate is colorless. So what does that tell you? Well, if your filtrate was green, it would mean that some of your nickel nitrate did not react and ended up filtering through. But because our filtrate was colorless, the filtrate color matches the ER color. So the filtrate color matches the ER color, okay, not the LR color. So again, that's really important too. So whatever color your filtrate is, it should match one of your two reactant colors. So if the filtrate came out green, it would tell us that not all the nickel reacted, and therefore it would be the ER. But because the filtrate came out colorless, that tells us that the sodium hydrogen phosphate is the ER, not the nickel nitrate, because there's no green anywhere in here, which means that the green all reacted to form our green precipitate up here. Okay, so your precipitate color will be connected to your LR color, and your filtrate color will be connected to your excess reagent. Those ions that didn't react are the ones that are making this color here. Okay, so your qualitative proof really is to look at your filtrate. Your filtrate color and your ER color will always match. If the filtrate color matches your LR, then you know you don't have the right excess reagent. Okay, so the last thing is, what are some experimental errors that give us efficiencies less than 100%? Okay, so the first one here is that your filter paper, your pore size, so those are the little holes in the filter paper, okay, are too large. So sometimes when they're too large, some precipitate passes through. And when some precipitate passes through, it's not collected in the filter paper, therefore it can't be weighed. And if it can't be weighed, it's going to lower your yield. Okay, so that's one reason why your efficiency would be less, is that some of your filter paper passed through and is in your filtrate and you don't notice it there, but it's enough that it's going to lower your yield. So this is a lower EY than the TY. This one we're going to do here is when you have a higher EY than a TY. Okay, so one is that some of your precipitate is going to pass through. Okay, another one is that not all the LR reacted. Okay, so therefore your maximum amount of precipitate wasn't made. And that happens sometime because reactants are unpredictable, and sometimes they won't fully react and you won't even notice it. Maybe there was a bit of green in that filtrate and you didn't even notice because it didn't all react. Okay, so if not all your limiting reagent reacted, your maximum amount of precipitate wasn't made. And if it wasn't made, it's going to measure out lower than what it should have been. Okay, the third one is that some precipitate, if it's sticky, will cling to the walls of the beaker and you can't get it off. So there'll be what's called residue. And if you get residue on the walls of your beakers and it can't be removed, it's not in your filter paper. And if it's not in your filter paper, it can't be measured. Okay? All right. And then the fourth thing that can happen is you get what's called a side reaction. So when a side reaction occurs, usually due to a contaminant, because not all chemicals sorry about that. Okay, a side reaction occurs usually due to a contaminant producing less solid, less precipitate, and more aqueous solution instead. So what might happen is where you expect two reactants to make solid, a contaminant makes its way in, a side reaction occurs, and instead of making precipitate, you make an aqueous solution, so you have less precipitate, and that will lower your overall yield. Okay, to get something higher, the most common reason why is that your filter paper and your precipitate are not fully dry. There's still some water in your filter paper that adds weight. Okay, it may feel dry to you, but it really isn't fully dry. So maybe you need to leave it for another day or two to make sure that it actually does dry. That is one of the main reasons why a percent yield is higher. The second one, again, is a side reaction with a contaminant. Where more precipitate is made. And less aqueous solution. Okay, so it's not that often that you get percent efficiencies higher than 100. They're actually pretty rare. And these are the main two reasons, is that they're not fully, the paper's not fully dry, your precipitate's not fully dry, and you get what's called a side reaction occurring. And sometimes when it occurs, you get more precipitate than what you should, which means that your EI mass is going to come out higher than what it should, which would give you a percent yield. So make sure that you go through and you review these reasons for errors. Okay, there's also other errors too that can occur, like personal errors, like let's say you spilt something, but those should be fixed. To say that you spilt some reactant and that's why you made less precipitate, that's really on you. That at college, that is not an acceptable error by any means. You would have to redo the experiment. They're what's called gross personal errors. But let's say you go back up here and you've got residue. There's not much you can do about that. You can rinse it and use as much water in the world. If it's sticking to the walls, you cannot get it off. There's nothing you can do about that. But if you've splashed something on the lab bench and you notice that, you clean it up and you start over. You don't just say, yeah, I spilt something. That's not acceptable. Okay, that's not doing your job and that's being careless. So it's not an acceptable error in any experiment. Okay, so make sure that those types of errors, mismeasuring because you don't know how to use something, ask for help so you know how to use something. Okay, so these are deemed acceptable errors. There's obviously more to get an efficiency less than 100 because there's always going to be some losses occurring as opposed to gains. Okay, so that's your lesson with this. I know the video is long, but I figured this would be much better than trying to explain all of this on paper. There are some practice questions on your sheet. I've asked you a couple of questions about the lab experiment, because in any chemistry lab, this is a really good experiment for someone to get you to do. Working with a precipitation reaction, determining yields, and determining where your errors are, and determining whether or not your efficiency of your reaction is good, why it's not good. Okay, so good luck with that. If you have any questions, please send me an email. Thanks.